alaikum wa rahmatullahi wa barakatuh. Welcome grade 8. Inshallah, we are going to study a revision about what we studied in the second term. We will study now the geometry part. So, first of all, we need to talk about what we already studied in the first unit in geometry, which is unit number 4. Remember the relation between the areas of two parallelograms. If you remember that, we talked about if you have two parallel lines and there's two parallelograms drawn between them. If they have the same common base, then and they are drawn between the two parallel lines, we can say that the two parallelograms are equal in area. Surface of two parallelograms with common base between two parallel straight lines, one is carrying this base, are equal in area. Like these two also here, we have here the parallel lines and the common base. Let's see another part here. A parallelogram with bases equal in length and lying on a straight line, while the opposite sides of these bases are on another straight line are equal in area. Like this here, BC and ZY are equal in length, then they are having the same area because the two lines here are parallel. If we have a parallelogram and a rectangle with common base between two parallel straight lines, they are also equal in area. Also, you have a relation between the two triangles and a triangle and a parallelogram. First here we have the relation between the two triangles here. If they have common base between two parallel lines, they are equal in area. And also we have if they are with equal bases and also between two parallel lines, then also we can say they have the same area. All these triangles are equal in area. If they have a common vertex or a median drawn in the triangle here, so the median, as you remember, divide the base into two equal parts, then we have now two triangles equal in area. They have equal bases and they almost have the same base, the same vertex here, which is the vertex. From it we draw the median. Then the median in a triangle, divide it into two triangles equal in area. Also, if we have here, as I told you, a common base, but they are separated like this with two equal bases and a common vertex, so we say the two triangles here are equal in area. Then you have to remember the relation between the triangle and the parallelogram if they have a common base between two parallel lines. As I told you, now you have to know that the area of the triangle equal half the area of the parallelogram if they have a common base and between two parallel straight lines. Let's study an example about this. First of all, we have ABCD is a parallelogram. E belong to the ray CB such that we have BC equals BE. We need to prove that the area of the triangle FEC, which is all this big triangle here, equal the area of the parallelogram ABCD. Okay, first of all, I will start saying that since ABCD, I'm explaining this so you can remember how to write a proof about this exercise. ABCD is a parallelogram. Then, of course, you know that AD is parallel to BC. And if so, and we have BC is common base. Common base in what? Common base in triangle FBC and the parallelogram ABCD. Then easily I can say that area of the triangle FBC equals half area of the parallelogram ABCD. Okay, I know that here if B is a median in the triangle FEC. Since we have FB is median in triangle FEC, I can say that then area of triangle FBC equals area of triangle FBE. the two areas here are equal and one of them is half the parallelogram, then adding them together it will be the full parallelogram. Then area of triangle FBC plus area of the triangle FBE will equal the area of the parallelogram ABCD, which means here area of the big triangle FEC equals area of the parallelogram ABCD. And that's it. Let's see another example here. ABC is a triangle. As you can see, the big triangle here. X belong to AB and Y belong to AC, M belong to BC, and you have XY parallel to CM or all BC. Prove that the area of the figure AXMY, which means this part here, equal the area of the triangle AXC, which is this one. As you can notice here, there is a common part between them, which is the triangle AXY, this one here. We can just not talk about it and try to talk about the part XYM and XYC. Yes, as you can notice, there is a common base between them, which is XY, and they are already between two parallel lines. Then I can say they are equal in area. I will start saying that since XY is parallel to BC, all BC here, and CM is common, not CM, we need XY to be the common base here, and XY is common base, then area of triangle XYM equals area of triangle XYC, and here we will just add area of the triangle AXY for both sides. Then now I have area of the figure AXMY equals area of the triangle AXC. And that's it, and proving the equality of these two areas. ABCD is a quadrilateral in which AD is parallel to BC. E belongs to the ray BC here, yes, and AC is intersecting with BD to get the point M. MC parallel to DE. Prove that the area of the triangle AMB, which is this one here, equal the area of the triangle MCE, this one here. Okay, it's like two parts are connected here and there is one triangle is common between them, which is this one. In the first quadrilateral ABCD, you have the two parallel lines. Between two parallel lines, there is a common base. Then you can say the two parts here are equal in area. The two triangles are equal in area. And talking about also the two parallel lines here in this part, you also will have two triangles equal in area. Let's try to say it here. We will say that since AD is parallel to BC, I can say any of the two lines is common base, AB or BC. It's up to you. So we will say that AD is common base here. That means area of triangle ADB will equal to area of triangle ADC. And if the two areas here are equal, I can just subtract area of triangle ADM from both from both sides here. Then we will say that area of triangle AMB equals area of triangle DMC. And this is number one. Talk about the other part here. Since we have DE is parallel to all AC or CM, we need only CM. And since we have CM is common base, then I will say that area of triangle DMC equals area of the triangle EMC. This is number 2, and you of course can notice that there's a triangle here is common between them, DMC, and also there is DMC here also. I can just remove this common one, then area of triangle AMB will be equal to area of the triangle EMC. EMC, which is the same as MCE, by the way. So that's what he's asking you to prove here. Let's see another part here. Talking about areas and perimeters of some geometric figures. Before that, you know that you already studied some of these figures like triangle, parallelogram, rectangle, square. You already studied this in the previous years. So getting the perimeter of any triangle, it will be sum of all the side length. Perimeter of parallelogram, sum of any two adjacent length, adjacent to any two adjacent sides, multiply the result by 2. Like the rectangle, length plus width multiplied by 2. This is the perimeter of rectangle. And the perimeter of the square, of course, side lengths multiply 4. What about the area? To get the area of the triangle, you have to multiply half by the base, multiply its corresponding height. Half times base times its corresponding height. Area of parallelogram, base length multiply its corresponding height. Rectangle, length multiply width, and the square, its side length to the power 2. Another figure here, it's the rhombus. To get the perimeter of the rhombus here, it will be side length multiply 4. And its area will be using one of the two rules. Side length multiply its height, its corresponding height, or half multiply the product of the lengths of the two diagonals, diagonal 1 and diagonal 2, or he called them here R1 and R2. And how to get the perimeter of the trapezium? Just add the sum of all the four sides here to get their sum, to get their the perimeter for the trapezium. But to get the area, it will be half multiply sum of the lengths of two parallel bases multiplied by the height. Half multiply the sum of the two parallel bases, we call it the middle base. So it can be just length of the middle base multiply height. And you have to remember that in the isosceles trapezium, the two base angles of it are equal in measure, and the two diagonals of it are also equal in measure. This is in trapezium. And here's some examples to solve it. Find the diagonal length of the square whose area is 18. How to get it? Okay, I know that the area of the square, it can be found using one of two rules. It can be length to the power 2 or half multiply diagonal to the power 2. Because the two diagonals of the square are equal in length, I will say that half diagonal power 2. Then the area will be half multiply diagonal power 2, which already equals 18. Okay, I need to get the diagonal here, then I will multiply by 2. Both the two sides, diagonal power 2 equals 36. Taking square root here, then the diagonal will be just 6 centimeters. Because he's asking about the length of the diagonal. Then, a rhombus, the product of its two diagonal length is 72. This is the product of the diagonals, and the height is 9. Find the side length. Okay, to get the side length, I first of all need to know the relation here between the diagonals and the height. And the side length, it's all related to the area. Yes. So the area of the trapezium, of the rhombus, sorry, it will be half multiply diagonal 1 multiply diagonal 2. He said that the product of the two diagonals is 72. So just half multiply 72. This is the area here. Half of 72, if you try to get this result here, it will be 36. Okay, now I know the area, and the height is 9. How to get the side length? Okay, the length will be the area divided by the height. So it will be 36 divided by 9, which equals 4 centimeters. Of course, the area here is square centimeter. And that's all for this part here, the square and the rhombus. Let's take another exercise about the trapezium. A trapezium whose area is 180 square centimeter. The ratio between the lengths of its two parallel bases, 3:2, and its height is 12. What is the length of each of the parallel bases? Okay, I know that the area equals half multiply sum of the two parallel bases, base 1 plus base 2, multiply height. I know a ratio between them. So if I want to say that base 1 may be equal 3x and base 2 may equals 2x. So now I have the base 1 and base 2. And this is the ratio, using the ratios here. I don't know this x, it's just a value. When we try to simplify them together, it became 3:2. So now we need to know this value x to get the length of each base of them. Okay, I know that the area is 180 equals half multiply 3x plus 2x all multiplied by the height, which is 12 here. Okay, 3x plus 2x, it's 5x, yes, so I have half multiply 5x multiply 12, which equals 180. Half multiply 12 equals 6. 6 times 5 equals 30. Now I have 30x equals 180. Try to divide by 30. X will be 10 divided 3 equals 6 only, because we don't know it now. We just put it here, substitute for it. Base 1 equals 3x, which is 3 multiply 6, which is 18 centimeter. And base 2 will be 2 multiply x, which is 2 multiply 6 equals 12 centimeter. Of course, if you want to make sure it's the correct answer or not, just add them multiplied by half and then multiplied by 12 to get the area. If it gives you the same result, then you are correct. Let's see another part here. It's about unit number 5, the similarity. You studied two kinds of similarity, similarity of two polygons and similarity of two triangles. How to prove or how to say the two polygons, when to say the two polygons are similar, when you have the two conditions together, which are that their corresponding angles are equal in measure and their corresponding side length are proportional. And be careful about this word, they are proportional, not equal in length. And in the triangles here, one of them, that's enough to say they are, any one of them is verified. That's so enough to say the two triangles are similar. So in the polygons, it's said to that the two polygons are similar if the following two conditions are verified together. It's said the two triangles are similar if one of the following two conditions is verified. One of them will be enough, the angles or the sides. Here are some remarks, some important remarks you have to remember. In the two similar polygons, the constant ratio among them, we call it ratio of enlargement or the drawing scale. If this ratio is greater than 1, then we are making polygon 1 enlargement of polygon 2. If it's less than 1, polygon 1 is minimizing of polygon 2. And if it's equal to 1, then they are congruent to each other. Polygon 1 is congruent to polygon 2. If the two polygons are similar, then their corresponding angles are equal in measure and their sides are proportional. Like here, triangle ABC similar to triangle DEF, so the angles here are equal, the corresponding angles. It means angle A equal to angle D, angle B equal to angle E, C is equal to F. That is the meaning of the word corresponding. And the sides also are proportional. Of course, the order of the vertices should be kept in giving names on similar polygons. And the congruent polygons are similar, but it's not necessary similar polygons to be congruent. If each of two polygons is similar to a third, they are similar. Any two regular polygons, the word regular means they all have the same equal basis and equal sides. All the sides are equal in length and all the angles also are equal in measure. So any two equilateral triangles are similar. Any two regular polygons of the same number of sides are similar. That means equilateral triangles are similar. Squares are similar. All the squares, by the way, are similar. But not rectangle, because rectangle is not a regular quadrilateral. The regular quadrilateral we know is the square. Any regular pentagon, all the regular pentagons are similar, or regular hexagons are similar, and so on. The two right angle triangles are similar if the measure of an acute angle, if we have only one angle, except the right, of course, equal to its corresponding in the other triangle, we can say the two right angle triangles are similar. Also, the two isosceles triangles, if there is only one angle in the whole triangle here equal to its corresponding, we will say the two isosceles triangles are similar. The ratio between the perimeters of two similar polygons, of course, equal to the ratio between the lengths of two corresponding sides. Let's have an exercise about this. The figure ABCD similar to the figure XYZL. Before going to the draw or the graph here or the figure, we can get what we need here from this part, from the similarity. Since they are similar, I will say that since ABCD is similar to XYZL, I will say that measure of angle A, of course, equal angle X. Angle B equals angle Y. Angle C equals angle Z. And angle D also equal angle L. Okay, but I don't know which one he needs me to get. He needs angle BCD. BCD is this one. So yes, it will be like angle Z. Really? Let's see. BCD here, it's like YZL. Yes, that's correct. It will be like angle Z. So I don't have any of them, so I will try to get all the angles here. Then measure angle A equals measure of angle X. I'm not looking at the drawing here or the figure. I just get it from the letters I have here. I have the measure of angle A already, so I can just write it, which equals 125 degree. And also measure angle B equals measure of angle B equals Y. Yes, which equals 70 degree. And measure of angle C equals measure of angle Z, which I don't have any of them. And also measure of angle D equals measure of angle L, which equals 80 degree. Now I have 3 angles of the 4. Then measure of angle C, which equals measure of angle Z, which he's asking you to find. It will be all the 360 minus the sum of these angles, 125 plus 70 plus 80. Now just add it using calculator and subtract the result from 360, which will be 85 degrees. Then the result here, it will be 85 degrees. Find the length of XL. Okay, we know that the side should be proportional. Since they are proportional, that means here AB over XY equals BC over YZ, CD over ZL, and of course AD over XL. We will try to write this here. Since also we said the two polygons here are similar, of course we are going to say that also here let's say first AB over XY equals BC over YZ, which equals CD over BC over YZ, yes, and CD over ZL. And finally here AD over XL. I don't have AB, I don't have XY, I don't need it already. BC, we have it's 8 over YZ, which is 2.4, seems to be the ratio that will help me to get what I need. CD and ZL, I don't have any of them and I don't need it. So I have AD, which is 6 over XL, which I need to find. Now just make cross multiplication to get the value of XL. It will be 6 multiply 2.4 divided by 8 to get the result, which will be 1.8 centimeter. Yes. And that's it here. Let's see another example here. ABC is a triangle in which AB equals 5 centimeter, BC equals 6 centimeter, AC equals 4 centimeter, AD equals 3. Prove that triangle ADE is similar to the triangle ABC. So we need to prove this triangle here is similar to the big one. I have the angles, I can use them to prove the two triangles are similar. He didn't say the two sides are parallel, but that's obvious here. We have two parallel sides here. So I can use the sides to prove they are similar if I have all the three sides of all the three triangles, the two triangles, all the three sides of each one of them. Then I can make proportionality. If they are proportional, all the three sides are proportional, then I can say they are similar. But since I don't have all the three sides for any of them, I will use the angles. We will say that since ED here is parallel to BC. If you can see here, we have the two lines here are parallel, and we have also, let's say, AB is transversal. Yes, as you can thinking now, it will be here you have the letter F. Then we will say that measure of angle B equals measure of angle ADE, which, because they are corresponding, we just write it here, corresponding. And also on the other side, if we have here AC is the transversal, we will say that measure of angle C equals measure of angle AED. They are also corresponding. Also, we can say one more angle, which is angle A here is the common angle, but you can just prove it with only two angles of them are equal to their corresponding. That's enough. If you wanted to put the third angle, it's okay, it's up to you. Now I will say that then triangle ADE here is similar to triangle ABC, and that's the first part. So we proved that the two triangles are similar. To get the length of any of DE or AE, that will be as a result of proving the two triangles are similar. We will say that then we have the proportionality, which I will find also from the names of the two triangles, like then AD over AB here equals DE over BC, which should be the same as AE, the third side here, and over AC. That's the proportionality, which is as a result of proving the two triangles are similar. Then what? We will just substitute for the sides here to get the result we need. We need DE and AE, so these two ratios will be missing numbers here, but this one will be of course complete. So AD here is 3 over AB, which is all is 5 centimeter, equals DE, we need to find it, over BC, which is 6, equals AE, which is missing number also, over all AC, which is 4. Okay, to get any of them here, if I want to get DE, I will multiply 3 by 6, divide the result by 5. Then DE will be 3 multiply 6 divide by 5. Also, to get AE, I will do the same. Multiply 3 by 4 and divide by 5. 3 times 4 divide 5. Okay, let's get the result of each one of them here. It will be, this one here, it will be 3.6, and here this one will be 2.4. Don't forget centimeter and centimeter. That's it for this part. Let's see another part here. Remember the converse of Pythagoras theorem. You already studied Pythagoras theorem in grade 7. So the converse of Pythagoras theorem, I will remind you of Pythagoras theorem itself. So when you have a right angle triangle, if it's already right, then to get any side of the three sides here, for example, let's get the length of AC. So AC squared using Pythagoras theorem, it will be AB to the power of 2 plus BC to the power of 2. If I want to get any of the two sides of the right angle, it will be AB to the power of 2 here will be just AC, the hypotenuse, minus the other side, BC power 2. And of course, if you want to get BC to the power of 2, it will be also the hypotenuse minus the other side. This is Pythagoras theorem. So what is the converse of Pythagoras theorem? The converse of Pythagoras theorem, if you already have this relation is satisfied, this one here, the hypotenuse or the longest side square or the square of the longest side equal the sum of the squares of the other two sides, then I can say the triangle is right. Let's see here. After that, you already studied the projections. Okay, the projection of a point on a straight line, let's start with it. If we have a point like this, if you wanted to drop a perpendicular from this point to the opposite side, it will be at a point, just a point. What if I have a line segment? To drop a perpendicular from this line segment, I will drop from the starting point and from the ending point. Each perpendicular here is at a point. Here, for example, it's A, it will be here at A dash. If it's B, for example, it will be B dash. So the projection of the line segment AB, it will be the line segment A dash, B dash. But the projection of a point is just a point. So the projection of a line segment, it will be also a line segment like this here. The projection of a ray, it will be also a ray. The projection of a straight line, it will be a straight line. Let's see by details here. If I wanted to drop a point from A and B, as I told you here, A dash and B dash, each one will drop a perpendicular. If it's parallel to the straight line, their length will be equal. They will have the same length. But if they are not parallel, it will not have the same length. Here they are not parallel, but one of the 2 points is already on the straight line, so its projection will be itself. The other one is another point. Here also it's intersecting like this, so it will be also 2 points, which is a line segment. That means they have length. The length of the projection of a line segment will be less than or equal to the length of the original line segment. Only in one case, which is the line segment perpendicular to the straight line. If it's perpendicular, both the 2 points their projection will be a point on the straight line. Then its length will be 0. So here, as we were talking, the projection of a ray will be a ray, subset from the straight line. Only in the case of this ray is perpendicular to the straight line, its projection will be a point belonging to the straight line. The same with the straight line. Projection of a straight line on a straight line, its projection will be also a straight line. What if it's perpendicular? Yes, they both will be at just one point. So the projection of a straight line perpendicular to it, it will be a point intersecting it will be the point which is the intersection point of the straight line. That's here the projection. Let's go to talk about the Euclidean theorem. You know that Euclidean theorem is the most important thing here. It will help you to solve many exercises in this year and also in the next year, inshallah, and the next years after that, because it's as important as the Pythagorean theorem. So you can only apply Euclidean theorem when you have a right angle triangle and there is a perpendicular from the right angle to the opposite side or to the hypotenuse. So in the right angle triangle, the area of the square on a side, this is the text of the theorem, on a side of the right angle is equal to the area of the rectangle whose dimensions are the length of the projection of this side on the hypotenuse and the length of the hypotenuse. Again, so you have to recognize this text. The area of the square on the side of the right angle, if you try to draw a square here, its area will be what? Will be the area of the rectangle whose dimensions are the length of the projection of this side. This is the projection of this side on the hypotenuse, and the length of the hypotenuse itself. That's the area of the square, which is AB to the power 2, will be BD multiply BC. Multiplication, the product of the two dimensions here. So let's revise the rules of the Euclidean. When we have a triangle ABC, which is the right angle triangle at A, and there is a perpendicular from A to the hypotenuse BC, it's AD here. How to get the length of these sides, which is AB to the power 2. AB, so I came from the right angle here to the other point, so it will be BD multiply BC. You have to keep it in your mind, BD multiply BC. What if I want to get AC? It will be the same idea, AC to the power 2, CD multiply CB. What if I want to get AD to the power of 2 also? AD here to the power of 2, it will be the multiplication of the two parts of the hypotenuse here, BD multiplied by DC. There is another rule to find the length of AD without the power here. It will be just AD. We got it from the similarity between the two triangles here and the three triangles, by the way. You have to know this first also. If there is a perpendicular from the right angle, in the right angle triangle, a perpendicular to the hypotenuse here, this perpendicular divide the triangle into two triangles similar to each other, and they are similar to the original triangle. From similarity, we got that AD equal the multiplication of AB times AC, divide the result by BC. So AB times AC, divide the hypotenuse BC. These are the four rules of Pythagoras, and they are very important. AB power 2, BD, BC. AC power 2, CD, CB. AD power 2, DB, DC. And to get AD with another rule, multiply the two sides here, AB, AC, divide by BC. Let's see an example about this. We have here triangle DBA. He said that this triangle here is similar to triangle ABC. This exercise is getting or trying to gather between all the projections and the similarity, and also the Euclidean theorem, and maybe Pythagoras also. Let's see here, DBA similar to ABC. Measure angle BAC here is 90 degrees. Prove that AD is perpendicular to BC. How to prove they are perpendicular here? If they are perpendicular, that means this angle here should be 90. Okay, let's use similarity to get this. We will say that since triangle DBA is similar to triangle ABC. Okay, which two angles you think they are equal? I will try here. I need angle BAC, this angle here, because I needed to see if it's equal to this angle or not. Using this one here, B, A, then C, So it will be B, D, then A. Then measure of angle BAC equals measure of angle, as I said, I started from the middle, then going to A, then C. So BDA. Is this the angle we are searching for? Yes, BDA is this angle here, which will be 90 degree. Then, of course, AD is perpendicular to BC. That's the first thing he is asking you about. Then he said that if AB is 8 centimeters and AC is 6 centimeters, of course, before we complete doing anything, angle A is right, then we will say that since measure of angle A equals 90 degree, and you know that AB is 8 centimeter and AC equals 6 centimeter, of course, using Pythagoras, you can get BC. Then BC equals square root 8 to the power 2 plus 6 to the power 2, which equals 10 centimeter. And this is the first thing he's asking you about. So use Pythagoras to get the third side. Then let's see the length of the projection of AB on BC. Let's first here write what we got here. This is 10 centimeter. We need to get the length of the projection of AB on BC. Length of projection of AB on BC, I think you know it, but let's try to get it. I will just write this here to start solving the projections here. So what will be the projection of a line segment AB on the straight line BC? First of all, to get the projection, try to get which letter is repeated here. A, B, B, C. Yes, I noted that B is the repeated letter. Then let's get the projection of A on BC. From A, which perpendicular I dropped from A on BC? Direct, the perpendicular, we just proved it. Yes, it's at point D. Then we will say that then BD is the projection of AB on BC. Okay, how to get now the length of BD? Okay, BD is only we can get using Euclidean, using the rule of AB. So we will say that since AB, of course AB to the power of 2, equals BD multiplied by BC. This is the only rule we can get BD in. Okay, I know that AB to the power 2, which is 8 power 2, equals BD. We need to find its length, multiply by BC, which is 10. So BD equals 8 power 2, which is 64, divided by 10, which equals 6.4 centimeter. That's the length of the projection of AB on BC. Finally, here we need you to find the length of AD. We have many methods to find the length of AD. We can find it using Pythagoras in this triangle. Also, we can get the length of CD, and then we can get it using Euclidean. AD to the power 2 will be DB multiply DC. If we have DB, it's 6.4. Subtracted from 10, you will find DC. It's another method. And also we can use the most easy method here because we have the three sides. AD will be AB multiply AC divided by BC. Then AB, which is 8, multiply AC, which is 6, divided by 10. 6 times 8 equals 48, divide 10, which will be 4.8 centimeter. And that's all what he needed here, and we got it all. The last part here, we are going to talk about classifying triangles according to their angles. You already studied this before in about the converse of Pythagoras theorem, which is when you have the longest side to the power 2 equals the sum of the squares of the other two sides, then yes, the triangle is right. What if this longest side is more than the sum? If it's more than the sum, the angle will be obtuse, or the triangle now is obtuse angle triangle. If the side here is less than the sum, then it will be acute. Okay, you have to notice that which angle is the acute, which angle is the obtuse, which angle is the right. With the angle which is opposite to the longest side here will be the right one. The longest side here is AC, so its opposite angle, which is B, will be the obtuse one. But in acute, you don't care about it because all the angles now will be acute. In any triangle, you have to remember that in any triangle, have at least two acute angles. Any triangle have at least two acute angles. If they are only two, the third one may be right or obtuse. What if the third one is also acute? Then the triangle is acute angle triangle. Here you have to first get the square of the length of each side and then compare between the square of the length of the longest side and the sum of the squares of the other two sides. Now you can determine the type of the triangle according to these informations here. We also have to do the steps to determine the type of the angle in any triangle, any angle, not just the angle opposite to the longest side. And the greatest angle in measure, this is the angle which is opposite to the longest side, and the smaller one is the one which is opposite to the shortest side. And as I told you, there are two acute angles at least in any triangle. And a last exercise here, AB equals 6 cm, BC equals 8 cm, AC equals 9 cm. Let's determine the type of the triangle according to its angles. So first of all, I have to get the longest side squared. It will be 9 squared, which is 81. Also, let's get the sum of the other two sides squared, AB power 2 plus BC to the power 2, which is 6 power 2 plus 8 power 2. Here it's 36 plus 64, which equals 100. So now that's obvious. AC to the power 2 is less than the sum of AB to the power 2 plus BC to the power 2. If the longest side is less than the sum of the other two sides, we will say that the triangle or triangle ABC here, it's called ABC, is acute angle triangle. Here is another exercise. Determine the type of the greatest angle in the triangle ABC. He needs the greatest angle, not the type. Of course, the type of the triangle will be determined using the greatest angle. So the greatest angle, of course, will be opposite to the longest side, which is AB. Then I have to get AB to the power of 2, which equals 8 power 2, which is 64. And then get the two other sides squared and get their sum. BC to the power of 2 plus AC to the power of 2, which equal 36 plus 25. Just adding them, 6 plus 5 here is 11. 3 plus 3 equals 6, so it's 61. That's obvious now. 64 is more than 61. Then AB, the longest side here, will be more than the sum of the other two squares of the other two sides. If it's if it's more than the sum, then the opposite angle here, which is angle C, the missing letter here is C, is obtuse angle here, which means triangle ABC, of course, is obtuse angle triangle. Let's see another example. Identify the type of angle B in triangle ABC. If AB is 7 cm, BC is 12 cm, AC is 8 cm. So to get the type of angle B, it's not the angle which is opposite to the longest side. No, it's just angle B, which is opposite to angle side AC. So first of all, I will get AC to the power of 2. 8 power 2, which is 64. Then let's get the other two sides squared and their sum. AB to the power of 2 plus BC to the power 2, which is 49 plus BC power 2, 12 power 2, 144, which equals here 13, 5 plus 4 is 9, 193. That's obvious here. AC to the power of 2 is less than the sum of the squares of the other two sides. And if it's less than the sum, then the opposite angle, angle B here, is acute angle. Then he is asking you to determine the type of the triangle according to its angle. Determining the type of the triangle, it's not depending on any angle, just any angle like that and get its type. No, you have to get the longest side, which is opposite to the greatest angle. If we get the type of the greatest angle, now we know the type of the triangle. We will say that since we have here BC to the power of 2, which is 144, this is the longest side. Now we get AB power 2 plus AC to the power of 2. AB power 2, which is 49, plus 8 power 2, which is 64. Here it's 113. Now I know that this side BC to the power of 2 is more than the sum of the squares of the other two sides, AB power 2 plus AC to the power of 2. If it's more than it, then angle, the opposite to it is angle A. I can write angle A is obtuse, or I can say that triangle ABC is obtuse at angle A, which is opposite to BC. And that's all for now. Thank you for watching. Wish you enjoyed the session, wish you understood what we revised today. Thank you for watching. See you another time, inshallah. Goodbye.